guys, so the last section was about how we would do the first-hand investigation of heat of dissolution. So just to recap, what we did was we have a known amount of water, we take the temperature of it, record it down, we put in the solute, whatever we were measuring, dissolve it, mix it up, and then take the final temperature. We use the change in temperature and what we know about the heat capacity of water to then determine how much, whether the dissolution of the salt was either exothermic or endothermic. So when we left off, we just finished off with one of the calculations. So we'll just continue on with the next calculation, which is sodium hydroxide. We have 50 grams of water as our solvent, and then we put in 2 grams of the solute, which is the sodium hydroxide. So our mass is going to be 52 grams. The heat capacity of water is 4.2 joules per Kelvin gram, and the change in temperature was 9.4 Kelvin, or 9.4 degrees Celsius. So what we will then do, we have to use this to calculate the equation, calculate the delta H, which is 52. Remember the equation is, do you remember the equation? It's delta H equals minus mc, delta T. So here we have H minus M, 52, times it by C, which is 4.2 there, times by delta T, which is 9.4. And what you get is minus 2053 joules. Remember, 1 degree change is equal to a change in 1 Kelvin. So Q equals mc delta T, and we know that we need to calculate the mass of the sodium hydroxide. So sodium hydroxide, the molar mass is 39.998 grams per mole. Remember the equation N equals mass over molar mass. Substitute the 2, we had 2 grams of sodium hydroxide we added to the water. Divide this by the molar mass, and we get 0.05 moles of sodium hydroxide we used. Divide our initial, what we first calculated as our delta H, divided by our molar, a number of moles, and that means we get minus 41,060 joules per mole. So every time we would dissolve 1 mole of sodium hydroxide, this amount of energy will be released. And when we convert joules to kilojoules divided by 1,000, we get minus 41.1 kilojoules per mole. So next we will be looking at the conclusion. So the dissolution of ammonium nitrate was endothermic because remember the delta H was positive. The dissolution of sodium hydroxide was exothermic because the delta H here was negative. So our assumptions: the heat lost or gained by the solution was equal to the heat gained or lost by the substances undergoing dissolution. So we didn't lose anything out into the environment. That's our assumption. And the specific heat capacity of the solution is equal to the heat capacity of the water. So how valid was it? The results are valid if the assumptions we had before are true. The molar heat of solution refers to a large amount of water, but however we usually only use 50 grams, so we have to account for that. So our results may not be considered valid in this case. The accuracy. So we can increase our accuracy by using more insulation, so either a polystyrene lid or maybe double walling the cup, so 2 cups together. We can use a more accurate thermometer, so a digital thermometer, to give us more accurate readings of the temperature changes. We can use an electric balance, which will also give us more accurate weights. And we weigh in a dry environment because sodium hydroxide absorbs a lot of water from the air. So if there's a lot of water in the air, that means the weight of sodium hydroxide that we weigh out is a bit more than what we would expect it to be, and therefore our calculations will be out. So reliability. We can repeat the experiment. The more times we repeat it and the more times it's the same and consistent, we know it's reliable, our results are reliable and they're most likely true. We then have to average the results and compare values. So we can look into the textbooks or online and see that the delta H of sodium hydroxide is minus 44.5, which is very similar to what we had. Similarly, with the ammonium nitrate, was plus 25.8, which is also similar to what we had. So to sum up, this first-hand investigation led us to look at how does salts dissolve into water and whether they're exo or endothermic reactions. So in this case, the sodium hydroxide is exothermic, but the ammonium nitrate is endothermic. And when we know the changes in temperature, the mass of what we use, the specific heat capacity of water, we can then calculate the specific the number of joules that is either released or absorbed by the substance. So using that, we can answer just a few questions. Question 3, when 0.78 grams of sodium hydroxide is dissolved in 100 grams of water in an insulated cup, the temperature of the water rises from 21.5 degrees Celsius to 23.56 degrees Celsius. Calculate the heat of solution for sodium hydroxide. So this is really similar to what we did before. We use the equation Q equals MC delta T. And we look at how much is the mass of sodium hydroxide, which is 22.9 for sodium, plus 16 for the oxygen, plus the 1 for the hydrogen, which gives us 40 grams. So the number of moles is the mass over molar mass, and that's 0.78 grams, because that's what we measured out here, divided by the molar mass, which we calculated here at 40. And that gives us 0.0195 of moles. So we use the equation delta H equals MC delta T. And we know that the mass was 100 grams of water in an insulated cup, plus the amount we added of sodium hydroxide, which is 0.78, times it by the heat capacity of water, 4.2, times it by the change in temperature, which is 23.56 minus 21.5, gives us 2 degrees 0.06 that are the change in temperature. When we calculate that, we get 871.949. And to calculate the delta H solution, so per moles, we need the delta H that we had just calculated divided by the number of moles. So what we have is, we use this number we just calculated for delta H, divided by the number of moles of sodium hydroxide we added, which is here. And what we get is 447,155 joules, which is equal to 407.155 kilojoules, because to convert from joules to kilojoules, we need to divide it by 1,000. So next, question 4. When we have 2.07 grams of potassium hydroxide dissolved in 100 ml of water, the temperature of the water increases from 21.5 degrees Celsius to 26.4 degrees Celsius. Calculate the molar heat of solution for potassium hydroxide. So what we're doing is looking at potassium hydroxide, KOH, add up all the molar masses for all of these to get the molar mass of KOH. 39.1 plus 16 plus 1 gives us 56.108 or 56 grams. So remember, the number of moles is mass over molar mass. So we know the mass we measured out is 2.07 divided by the molar mass, which we just calculated here. And what we get is 0.0369 moles. We then use the delta H equals MC delta T to look at the heat of solution. So the mass is the 100 grams of water that we had, 100 mils of water. 1 mil is equal to 1 gram. So 100 grams plus the 2.07 of the potassium hydroxide, times it by the heat capacity of water, 4.2, times it by delta T, the change in temperature, which we do 26.4 minus 21.5, gives us 4.9. Calculate that, 2,100.6 joules. And then to get the heat of solution, we need to divide it by the number of moles because it's per mole. So this number from here, the delta H, number of moles we calculated up here, divide it and we get 56,926 moles per litre. And when we convert that to kilojoules, divided by 1,000 gives us 56.92 kilojoules per mole. Finally, question 5. What can you do to increase accuracy in our experiment? So we can use a better insulated container, such as a specific calorimetric container or a styrofoam lid in this experiment. This will allow us to keep the heat in so we don't lose any heat into the surroundings. Use a more accurate thermometer, such as a digital thermometer, because when we look at the ones with the red dye or the mercury, we can't really tell very small differences, but a digital thermometer can. And the use of a more accurate set of scales, such as a digital scale, so we can, which we then can measure milligrams or even smaller than that and get more accurate results, so then we can have better calculations. So in summary, the first-hand investigation, we have a known amount of water, put in a known amount of solute, and then measure the initial and final temperature. We can then calculate whether the dissolution of the salt is an exothermic or an endothermic reaction.